Here in this video, now we introduce the tool that was mentioned in the first video, L'Hopital's rule. So here it is, the statement of it, and this is the screenshot of what is the statement of L'Hopital's rule in your textbook in Stewart Calculus. So the beginning top part just gives some preamble, some conditions that we need in order to use L'Hopital's rule, but mainly what we're looking for is the function has to be differentiable and g prime not equal to 0. What we'll find later in this definition is g is the denominator function. But taking these, we find that, okay, if we have either f of x being 0 in this limit and g of x equals 0 in this limit, notice what they're going for is discussing the 0 divided by 0 form, or if they both are equal to positive or negative infinity. So that's our other indeterminate form that we discussed before, infinity divided by infinity. If either of these cases holds true, then L'Hopital's rule is exactly this statement down here. The limit as x approaches a of that rational expression is the same as the limit as x approaches a of the derivatives of those individual functions. So what we can find out about the original limiting behavior is the same as if we can find out what happens to the derivative of the top and the bottom individually. And just to be careful, note how we're taking derivatives independent of each other. This isn't the quotient rule. We're not taking a derivative of a quotient function or a rational function. We're taking derivatives of the individual parts of that fraction. So you take the derivative of the top and put that back on top, and same thing, you take a derivative of the bottom and put that back on bottom. And if that limit exists, then that is your limit of the original expression. So notice the original statement up here. We cannot let g prime of x equaling 0. That's because we still need this to actually be defined. So we're just kind of changing the look of the problem so that we can actually do something with that function. So let's go back to this example that we had trouble with. The limit as x approaches 1 of natural log of x over x minus 1. And again, the last video we found this was a 0 over 0 form. So it was indeterminate. We couldn't do anything with it. We couldn't factor it like the very first example, so algebra was kind of at a loss for us. But then we looked at the graph and saw that it seems like the limit did exist. It had the same behavior approaching 1 from both sides. Well, these two functions are continuous at x equals 1, and they are differentiable at x equals 1. So, how we usually write this, if we're going to apply L'Hopital's rule, then we just write this little L apostrophe H on the equal sign to say and justify why this equals is true. But we see that it's the same limit as x approaches 1, but we take a derivative of the top and the bottom individually. So remember, the derivative of natural log is the rational function 1 over x. So that is what the numerator turns into. And same thing, we take a derivative of the bottom portion. So the derivative with respect to x of x minus 1 is just 1. Okay, and if we simplify that expression a little bit, notice we're just dividing by 1 in the denominator. So in essence, it just goes away. And instead, we now get this limit as x approaches 1 of 1 over x, which is a nice limit to take because it's just 1 divided by 1, and that simplifies to 1, which is exactly the value we saw in the graph that we found in the earlier video. So L'Hopital's rule is a really helpful way to evaluate these limits. So in the next video, I'm going to introduce more examples of doing these. So we're now just going to do more and more examples of using L'Hopital's rule, getting used to taking derivatives individually, and when we're allowed to use L'Hopital's rule.